What? It's time for math class already? Let's do some math.
Calculus, early transcendentals. I can't wait to learn about calculus. You make me go mental. Logarithms aren't easy for me. When limits got you down and your mind won't work at all, don't worry about it, baby. Here comes L'Hopital. Calculus, early transcendentals, hyperbolic coaster catenary. Calculus, learn real world models when you make it to Calculus 3.
Hello once again, calculus students. The topic for today is rules of differentiation. At this point we've introduced the idea of the derivative and given its definition, but you've no doubt noticed that the definition of derivative can be a little difficult to use because it involves calculating limits and performing a lot of algebraic maneuvers. In today's lesson we're going to start introducing rules that make the computation of derivatives much easier.
Hello again. Today's lesson is on the rules of differentiation. So differentiation is just the process of computing derivatives. And what we want to do today is develop a set of general rules that we can apply to a wide variety of functions that'll make computing derivatives a lot simpler. Up to this point, all we have for computing derivatives is the definition of derivative, which involves the limit. It's the limit as h goes to 0 of f of x plus h minus f of x all divided by h. Well, yeah, that rule is unwieldy, especially when you're dealing with a complicated function. So in our usual way, we want to develop rules that we can apply to a wide variety of things and that apply to small things. So when we think of a function as being composed of a bunch of smaller pieces, we want these rules to be easy to apply to the small pieces, so we can break these complicated functions down. So let's start with the simplest kind of function there is, a constant function. So theorem 3.2 here says that the derivative of any constant is 0. Rules don't get much simpler than that. The derivative with respect to x of 14.73, that would be 0. The derivative with respect to x of pi, well, pi is still a constant. We know that it has a decimal approximation of like 3.1415, blah, blah, blah. But it's a constant. And because it's a constant, its derivative is 0. How about square root of 2? Is that a constant? Well, you can punch it in your calculator and you'll see that you get some decimal approximation of it that's always the same. So it's a constant. So if f of x is just the square root of 2 function, the derivative of that constant function is again 0. I like that rule. Easy to apply. I'm not going to go through and prove every rule that we come across, but I will prove some of them because I want you to get connected back to the definition of things and understand that all these rules can be deduced. They're not magical. So why is the derivative of a constant equal to 0? Well, let's take a quick proof. Let's see if we can prove it real quick. So I'm trying to prove that a constant function has its derivative is 0. So let me just make some notation here. Let's let f of x be our constant expressed as a function. Then we know how to compute the derivative of any function. F prime of x can be obtained by taking the limit as h goes to 0 of f of x plus h minus f of x over h. In the absence of any kind of in the absence of some kind of rule that we can apply, when we're developing rules of differentiation, we usually fall back to the definition of derivative. Okay. Well, now let's think about how a constant function works. So over here to the side somewhere, f of x is equal to this constant, what is f of 3? Well, you get c. And you're like, what's f of 17.45? That would be c. So it doesn't matter what you put into the function, f of x plus h, that's also equal to c. So in simplifying this fraction that we want to take the limit of, we notice that, well, the numerator just ends up being c minus c, because f of x plus h is c. F of x is c. That's all divided by h. Well, c minus c in the numerator is equal to 0, so we're taking the limit as h goes to 0 of 0 divided by h, but 0 divided by h is 0. So that's just 0. And the limit of a constant, we have a rule for that. The limit of a constant is that constant, so voila. All in all, this string of equalities here says f prime of x equals 0, which was what we wanted to show. So the next rule we have here is known as the power rule. The power rule is called the power rule because it has to do with differentiating powers of x. So x to the n here is, a power of x. So that's where the rule gets its name. And this is a great little rule. You'll probably use this rule as much or more than any other rule that you use in this class. It just says if you want to take the derivative of x to the n, you bring the exponent n down, and then you just reduce the power on x by 1. It's really easy to apply, and it works for any non-negative integer. So in other words, n can be equal to 0, 1, 2, and so forth here. We'll see later that the power rule can be generalized to work for any exponent, any real numbered exponent, but for now we're just going to do it for non-negative integers. So the derivative of x to the 4th, the way the rule works is whatever the exponent is, you bring it down, and then you reduce that exponent by 1. So it'd be 4 minus 1 there. Or in other words, 4x to the 3rd. Done. That's way easier than doing a limit thing. In the next example, y is x to the 100th. Well, x to the 100th really is no harder to do than x to the 4th, right? So y prime would be bring the 100 down, then you'd have x, and then reduce the exponent by 1, you get x to the 99th. This rule even works on y equals x to the 0. Well, x to the 0 is really just 1, right? So I know that if I take the derivative of x to the 0, I should get 0, but the power rule applies to it also. Y prime here would be 0 times x to the negative 1, but 0 times anything is 0, so you still get 0. All right. So I would like to present to you a quick proof of why the power rule is true. The power rule depends on a preliminary algebra fact, which tells you how to factor expressions of the form x to the n minus a to the n. In fact, you've seen specific versions of this rule before, like, for example, x squared minus a squared is equal to x minus a times x plus a. And you know that x cubed, maybe you know this one, x cubed minus a cubed is x minus a times x squared plus a times x plus a squared. Well, both of these are specific examples of the formula that's in green there. The important part of this rule is that you can factor out for x to the n minus a to the n, you can factor out x minus a in the front, and then you get this expression where the exponents, the powers of x are decreasing, starting at n minus 1 and going downward all the way till they get to 0 at the very end. And the powers of a are increasing. So the first term has an a to the 0 term, which is hidden, right? But you could imagine there's an a to the 0 right there. And then it goes a to the 1, a to the 2, all the way up to a to the n minus 1 by the time you get to the end. Armed with this algebra fact in hand, and if you're not sure about that algebra fact, one way that you can kind of verify it for yourself is to try to multiply it back out and then cancel terms that add to 0. But anyway, here's how that rest of that proof would go. So I would make f of x to be my function x to the n. F prime of a, we can use that limit as x goes to a definition of derivative. So it'd be f of x minus f of a, all divided by x minus a. And then this is where we got to use the rule in green there. So this will be the limit as x goes to a. Okay, f of x would be x to the n, because that's our function, right? F of x. And then f of a would be a to the n. And then in the denominator, you have x minus a. And you can see in the numerator there the expression in green on the left-hand side. So we want to take advantage of that. So in the numerator, we're going to replace it with the right-hand side of the expression in green above, and you get x minus a times x to the n minus 1 plus x to the n minus 2 times a plus x to the n minus 3 times a squared. And anyway, I'm just copying what I see above there. So anyway, wow, this looks really yucky and scary right now. But at least something good is happening. I can get my canceling stick out and cancel those x minus a's out. And the problem in the definition of derivative, the reason you can't do just direct substitution all the time is because you always get 0 in the denominator when you try to substitute in x equals a or h equals 0, depending on the version of derivative you're using. But now we've got that canceled off, and let's see what we got left here. So what we're left with is this x to the n minus 1 plus x to the n minus 2 times a plus x to the n minus 3 times a squared. So the powers on x are going down, the powers on a are going up. By the time you get to the n, it looks like x squared times a to the n minus 3 plus x to the 1 times a to the n minus 2 plus a to the n minus 1. And I can do this by direct substitution here. So this is going to come out to, well, just substitute a in place of x and you get a to the n minus 1 plus, then on the second term you're going to get a to the n minus 2 times a to the 1. In a situation like that, you add the exponents and you get a to the n minus 1 there too. And then the same exact thing happens on the third term. You'll have a to the n minus 3 times a to the 2. When you add the exponents, you get a to the n minus 1. And this happens for every one of these terms. Notice that we're adding together the same thing a number of times. And so how many of those things do we have? Well, we just need to count how many of those terms are in that original sum. It's not so hard to count them. If you just compare, like let's say we put a 1 beneath that first term, and then the next one I'm going to put a 2 under, and the third one I'll put a 3 under. Notice that whatever the red number is, the exponent on a is always 1 less than that. So by the time you get to that one where it's a to the n minus 3, that must mean this is the n minus 2 term, and the next one after that would be n minus 1, and then the next one after that's n. So just by counting, like I did in red there, I see that there are actually exactly n of those terms. So what I end up with at the end here are n of these a to the n minus 1s. And that's really the power rule, right? Except I've got a in place of x. So this tells me that f prime of x is n times x to the n minus 1. So there was sort of a scary looking algebraic expression that we had to take advantage of, and you might be thinking, well, how would I have known about that? Well, maybe not. Maybe you wouldn't have known that about that one off the top of your head. But, these are the sort of things you can look up. You can look up these kind of formulas in sort of encyclopedias of these kind of facts. So if you were really determined to prove it from scratch and you didn't know that, you might have been resourceful and looked it up somewhere. All right. So anyway, that's the power rule. Next general rule that we'll have for computing derivatives is called the constant multiple rule. This one is just saying that when you want to take the derivative of a constant times a function, you can just pull that constant out, assuming that the function f of x is differentiable. So, f of x by itself might be something that's easy to differentiate, like maybe you can apply the power rule to it. So if you got a pesky constant multiplied out in front of it, it's not a big deal. You just pull it out of the way and then compute the derivative. So for example, this very first example on the top left here, if I want to compute that derivative of 3 times x to the 5th, first thing I could do is just pull the 3 out of the way, and then I'm taking the derivative of x to the 5th. And then we just saw how to do derivative of x to the 5th. I can apply the power rule. So that'd be 3 times, and now to do the x to the 5th derivative, I bring the 5 down and then reduce the exponent by 1 for a grand total of 15 x to the 4th. Now sometimes, like in the example on the right there, it may look like the constant multiple rule doesn't apply. Because I'm dividing by 14 here, it doesn't look like multiplication. But anytime you divide by something, it's the same thing as multiplying times 1 over that. So I can think of this as the derivative of 1 over 14, that's a constant, times x to the 7th. And now I can do exactly the same sort of thing I did a second ago, pull the 1 over 14 out, and now I'm going to multiply times the derivative of x to the 7th, which, to do, I would bring the 7 down, and then reduce the power of x to the 6th power. And then I could reduce 7 over 14 to 1/2. So this ends up being, if I want to write it in a more compact form, I could write it as x to the 6th over 2. Okay, so the constant multiple rule is pretty easy to apply. Pretty handy dandy. Got one more example there. Even if the constant is something weird like pi, the constant rule doesn't say anything about that the constant has to be a perfect whole number integer. I mean, it can be any kind of weird constant. Square root of 2, e, something weird like that. So f prime of x for this third example here would just be pi. Now, usually we don't make such a big deal out of showing how we pull the constant out and everything. Usually we just do it. Like I'm going to pull the pi out mentally, and then I'm thinking, okay, I got to bring the 3 down. So I'd probably write that as 3 times pi times x squared and just jump straight to the answer like that. So maybe now I'll fascinate you with the proof of the constant multiple rule. You know, if these proofs are distracting you from the content of just calculating derivatives, you can skip over it for now. I would encourage you to check out these proofs, though. I think that understanding how things work give you some deeper insight into things, and sometimes having a little deeper insight can help you. So to do this proof, we need a function that looks like a constant times the function f of x. So I'm going to make a function, let g of x equal the constant times f of x. And we need to assume that that function f of x is differentiable. So that just means that I can compute that limit that gives you the derivative of f. If I run across that limit, I know that it, exists and it equals f prime of x. So then now I can, since I have an expression for the c times f of x that I'm calling g, then what I'm really wanting to do is compute g prime of x. Well, that would be the limit as h goes to 0 of g of x plus h minus g of x, all divided by h. And g of x plus h just means put x plus h in the formula that I have for g there, right here. And then in turn, all that means is put x plus h in the f function there. So you end up with c times f of x plus h minus c times f of x, all divided by h. And then what I'm going to do in the numerator is factor out that c, which I could write like this. After I factor it out of the numerator, I could just set it out in front of the fraction like this. So it'd be c times f of x plus h minus f of x over h. Now we had a limit rule way back when we did limit rules. I can't remember if it was limit law 2 or limit law 3. But one of those limit laws said that when you're taking the limit of a constant times something and you know what the limit of that other something is, you can pull the constant out. So I can do that here because when I pull that constant out and I look at the limit that remains, does it look familiar? What is the limit as h goes to 0 of f of x plus h minus f of x, all divided by h? That's right. That is the derivative of f. And what did we assume about f at the beginning? We assumed that f is differentiable. That means that that limit exists. And since it exists, I can go ahead and call it f prime of x. So this is equal to c times f prime of x. And that's what we wanted to show, right? Because we were trying to show that the derivative of this function g, which is just the constant times f of x, is c times the derivative of f. So we can pull the c out. So that's it. C'est fini. Oh, good, the sum rule. You notice that these rules are kind of going just like the limit rules went, right? Like there was a rule for taking the limit of sums and differences of functions, and there was one for pulling out the constant like we just did. Eventually we want to do products of functions and ratios, quotients. Let's have a look at this sum rule here. All it says is that if you got two functions, f and g are differentiable, then to compute the derivative of the sum of the two functions, you can just break that up as doing the derivatives of the two functions separately. Well, that's good. So like, for example, if I want to take the derivative of that 3x to the 4th plus x squared over 3, well, that sum rule tells me I can just break that up as the derivative of 3x to the 4th, and then separately I can do the derivative of x squared over 3. And both of those derivatives we know how to do from what we've learned previously. That first derivative, I can pull the 3 out and then bring the 4 down. When I bring the 4 down and multiply it times that 3, I'm going to have 12. And then I'm going to reduce the power on the x by 1, so I got 12x cubed plus, and then for the x squared, I can think of that, dividing by 3 is the same as multiplying by 1/3. So I've got a constant multiple of 1/3. I'm going to pull that out of the way. Then I'm going to bring the 2 down and multiply it times that 1/3, so I'll have 2/3. And then x, and then the power comes down to 1. And that's it. For the second example, we'll handle it similarly, but this is a subtraction problem, and our rule seems to only apply to sums. But can't we think of this as really doing the derivative of 2x to the 7th plus minus x over square root of 2, like that? Subtracting is just adding a negative. So really, when you see subtraction, that's really just addition with a constant multiple of -1. And then, we could just go ahead and calculate the derivatives of the two separate pieces there, and we'd get 14x to the 6th plus, and then we're going to get a -1 over square root of 2. So I'll just write that as -1 over square root of 2. And then the power on x gets reduced from 1 to 2. I'm sorry, it gets reduced from 1 to 0. But x to the 0, I'm not going to write x to the 0, because what's another way to write x to the 0? X to the 0 is just 1, right? And you usually don't go around saying times 1. So I'm just going to leave it like that. So this example points out that any subtraction problem, we can just convert it to addition. And so the sum rule would quickly give rise to a difference rule. So I'm going to go back up to the rule, and I'm going to put a minus under the plus there to indicate that this is really a sum rule. It's a difference rule also. And of course, it could happen that we have more than two things being added and subtracted together. So we can state a sort of generalized sum and difference rule here. So this just says that, if I'm adding 3 or 4 or however many functions together and I know how to differentiate each of them, I can just break up the derivative of the sum and difference up into the individual pieces. So in the example I have at the bottom there, I've got 3 functions being added and subtracted. And then to get the derivative, I can just go through and do the pieces. So the derivative of the first piece would be 32, x to the 3rd. The second piece, I'd bring the 3 down. It would cancel with the 3 in the denominator, so I just get minus x squared. And then the derivative of that 17x would be just plus 17, x to the 0. All right. We're really starting to make some progress here. We started out today only knowing the definition of derivative. Now we know how to differentiate constants, powers of x, and powers of x multiplied times constants, and now we can add all these things together and get basically any polynomial. So at this point, any polynomial in the world, you could differentiate it. So we're making progress. We'd still like to be able to differentiate rational functions and other kinds of weird functions like sine functions and things with square roots. And we're getting there. We're going to make an unexpected little detour here and talk about the natural exponential function. So the natural exponential function is this f of x equals e to the x function. That's called the natural exponential function. Or sometimes it's just called the exponential function. It's like the standard exponential function. You can have other exponential functions, like you can have like 2 to the x or 3 to the x. The base could be any positive number that you want. Heck, you could even have pi to the x. But it turns out that e to the x is the very nicest of all the exponential functions. Mainly, at least in the realm of calculus, one of the main reasons why e to the x is so nice is because look at this derivative formula here. It has probably the nicest derivative formula of any function. Maybe it's even better than the rule for constants. It just says the derivative of e to the x is e to the x. It's a function that when you differentiate it, you get back exactly the same thing. It turns out to be kind of difficult to give a really good, rigorous proof of this, so I'm not going to attempt it. The textbook does give some sort of hand-wavy explanation as to why it's true, but it depends on some sort of mystery stuff that you can't verify until later. So I'm just going to leave it and just have you take my word for it that the derivative of e to the x is e to the x. But if you accept that it's true, then we've got another little formula in our tool chest that we can use as needed. So for example, to take this derivative here at the bottom, well, it's a sum and difference of some different pieces, so I can break it up into the derivatives of the different pieces. And the first piece, 6x cubed, I would use the power rule along with the constant multiple rule. Pull the 6 out, bring the 3 down, so I get 18 x squared. On the second one, I can use the constant multiple rule, pull the -2 out. And then the derivative of e to the x is just e to the x. Doesn't get any better than that. And then the derivative of e to the 2 is e to the 2, right? I hope you didn't agree with me and say, right. No, that would be a fallacy. What kind of a number is e to the 2? That's right, e to the 2 is a constant. E itself is a constant because it's like 2.71 something. And then if you take that and raise it to the second power, you're going to get some other weird constant. I don't know exactly what. Something between 4 and 9. So the derivative of a constant is 0. So you get 0 is the contribution of taking the derivative of e to the 0. Of course, do we usually write plus a 0 at the end of something? Of course not. So I'm just going to get rid of that. Okay, so now we have another derivative formula, the one for e to the x. And yeah, as we go through this whole big chapter on derivatives, we will get to taking the derivative of sine and cosine and tangent. And we're going to get to taking the derivative of the logarithm. And we'll get to taking the derivatives of functions like 2 to the x and 3 to the x. And we'll get to taking derivatives of inverse trig functions, and we still got to get to the square root type functions. So all in good time, we'll get to them. Okay. So now, it turns out that you might want to take the derivative, and then whatever you get for the result, you might want to take the derivative again. So whenever you take the derivative multiple times, we call those higher order derivatives. So let's start at the beginning here with this. Let's suppose that we got our standard setup, or our standard general setup, where we got a function, y equals f of x. So that means we're giving the function two different names, right? We can call it y, or we can call it f. Now, our standard, our most basic, or the notation we introduced the derivative with was we used f prime. And we had some other notations we could use for that. We had y prime, and we had dy dx. I think for now I'll just mention those two. I mean, there were the capital D notation, there was some dot notation, but let me leave it at that for a second. Okay, so now the second derivative just means, so we use this 2 primes to indicate the second derivative. The second derivative just means take the derivative of the derivative. That's what's indicated in blue there. And that symbol that you see, there's a colon and then an equals. Whenever you see colon and equals, it just means we're defining it to be equal to this. So it's a definitional equals. So I'm saying f double prime of x is defined to be equal to the derivative with respect to x of f prime of x. So that's what we call the second derivative. And we have some other notations besides just putting 2 primes there that I want to mention. So we could also call that just like y double prime, but we might also use this notation, d2 dx of dx squared of f of x. So that d2 dx squared out here indicates the operation of doing the second derivative. Of course, anytime you're doing the second derivative, you can't jump straight to it. You got to first do the first derivative, and then you can, once you've got the first derivative, then you can compute the second derivative. I mean, we can also write this as d2y dx squared. There's another way to write it. And then we can similarly do the third derivative. The third derivative just means take the derivative of the second derivative. So of course we call that the third derivative. At some point, okay, we can do y prime here, but we might just write it like this too. Y, whenever we get tired of using, like, it wouldn't be practical if we were going to do the 40th derivative. Like I wouldn't want to have to go y and then put 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. This would be silly to put all these primes like this, right? So after a point, we just, maybe by the time we get to the fourth derivative, we put a parenthesis and then just put the number of derivatives that you want to take there. Or we might write this as d3 dx3 of f of x. Or we could write it d3y dx cubed. All these notations mean third derivative. And then, of course, by the time you start talking about some arbitrary nth derivative, it still means the same thing. Anytime you're doing an nth derivative, you're just taking the derivative of the previous derivative. So the nth derivative is the derivative of the n minus first derivative. And we would refer to that, same, we might do y to the n, or d to the n over dx to the n of y, or something like that, or dny over dx squared, dxn, something. So all these notations would be the same. as a matter of practice, probably we won't get past doing for most examples that you'll need in calculus, I can't think of any specific things where we need to go above about the third derivative, but who knows? It can come up in other scenarios that I'm not aware of that you need a fourth derivative. Who knows? So just to get the feel of it, let's start with this function y equals x cubed, and let's compute the first derivative, the second derivative, the third derivative, and the fourth derivative. Well, this should be pretty straightforward. Y prime would be 3x squared. Now y double prime would just mean to take 3x squared y prime and take the derivative of it. So that would be take the derivative of 3x squared. Well, bring the 2 down, multiply times 3, you get 6x. Y triple prime means to take the second derivative and then take the derivative of it. So that would be 6x prime, which would come out to 6. And the fourth derivative means take the third derivative and take the derivative of it. So that would be 6. Now take the derivative of that, and you get 0. Now, at this point, once you hit 0, all the derivatives after that are going to be equal to 0 too. Like the fifth derivative would be take the derivative of 0. You'd get 0. So I could, if I wanted to, go ahead and just say all the derivatives from 4 to infinity are equal to 0. Okay, so this is a pretty short lesson today. You now have some pretty good rules. At this point, you can compute derivatives of polynomials, any polynomial, and you could throw into the mix some constant times e to the x type pieces. But yeah, so in the next lesson, we're going to get into how do we do like rational functions? How do we deal with functions involving radicals? How do we do it whenever there's like two complicated functions multiplied together? So we have a sum and difference rule, but we don't have a product rule yet. So we'll need a product rule. And yeah, we'll want a rule for like how do you deal with a quotient so we can do those rational functions. So we need a quotient rule. And eventually we'll want to get a rule that tells us how to deal with when you compose two functions that you know how to differentiate. That'll be called the chain rule. We'll see that in a few lessons from now. So we're getting there though. We're starting to develop some rules, and very soon you will be able to calculate the derivative of just about anything, and you won't ever have to take a limit. It'll always be just this quick algebraic procedure, just like we were doing on this problem we just finished here. Okay, well, we'll stop there. Bye now.